Thanks so much for having me here. It's always a pleasure to be in Paris. And I'm going to talk about a topic that was introduced a bit yesterday by Paolo, because he was telling you all about the theory behind large deviations. And I'm just going to use it today to predict so-called counts in self-statistics. And most of this work has been done in intense collaboration with Francis, Sandrine, Christophe here, and also Paolo, of course. You've already seen him. And also with the help of expert simulators running the Horizon 1 simulation, to which we can actually compare. So the big question you might ask is, well, why should I be interested in counts in self-statistics? So first, I want to give you a short perspective, how we go from the cosmic microwave background that in some sense provide the initial conditions for structure formation to the cosmic web, and why we might think that actually counts in self-statistics are a clever clustering statistics to use. And then I will introduce a bit, again, the foundations of the large deviation theory and spherical collapse, and then I'm going to use it to show you predictions. And I will make the attempt to go from, well, theorist, dark matter description, tell you that you can probe cosmology, and in the end also convince you that you can actually apply this to real observables, namely bias tracers like galaxies. So let's see. Basically, the big question of cosmic structure formation is, how did the universe evolve from a nearly uniform initial state, so very uniform distribution of densities with very tiny fluctuation, into the rich structure we see in the cosmic web? And of course, the interesting question is also, how do we get those very, very large density contrasts we have around galaxies, like in the halos and the clusters, from tiny fluctuations that are of order 10 to the minus 5? And since this is an analytics workshop, the nice step in between is basically saying, well, at first order, those galaxies just trace the underlying dark matter, which provides the large-scale skeleton. So from this point of view, it's much easier to actually describe it, because we don't have messy baryons and we just have gravitational interaction. And we already heard a lot of talks about how we can understand the cosmic web as a whole, the skeleton and the specific structure and topology inside. So I will focus on something different today. So in the end, the question is, what can we actually learn from galaxy surveys? So we map galaxies in the sky and we have their redshift. So we basically have information not only about their distance, but also about the evolution of structure, namely the growth across cosmic time. So what you can basically see here is how the cosmic web assembles from, well, earlier times to later times. So in the end, we want to use this structure we see there to actually extract interesting cosmological information. And we need, well, at least if we think about it as theorists, we need two things. On the one hand, we want clustering statistics, because usually we don't really use those point patterns we extract from galaxy surveys, although I think Fabian will introduce this idea in the afternoon. So basically, we want to compress the information from this point pattern of the galaxies into clustering statistics that carry interesting information. And on the other hand, we need dynamics to predict those clustering statistics we measure. And we already heard a bit about perturbation theory by Leonardo in the beginning of this week. We can essentially apply this to small density contrast. But I will focus on something else. Maybe I want to take advantage of the spherical collapse solution, which is indeed the only analytical solution we know in the nonlinear regime. Of course, it's only before shell crossing, but I think Atsushi will talk a bit about how to go beyond that in the afternoon as well. So basically, if we think about it, we could make a wish list. What do we really want from what we have? So on the one hand, we want powerful statistics, because we want clustering statistics that have interesting information. And in particular, since we know that the late time distribution of matter is not Gaussian anymore, that means we don't just want two-point statistics like the power spectrum or the two-point correlation function, but something beyond. On the other hand, we want to be in an attractive or interesting regime. That means we want to describe regions that are very peculiar, so that have very low densities, like the voids Rien talked about, or the very overdense regions like the halos. And for example, Marcello told you about this. So, but on the third hand, what we want, since running simulations is kind of expensive and it's very hard to actually sample cosmological parameter space very well, we also want to have a very predictive dynamics that's preferably very robust and very simple. And if we could write down something analytically, that would be great, because this way it's very easy to vary cosmological parameters. And I'm not saying that we should replace numerical simulations at all, but we can maybe think a bit about, can we use special statistics for which we can predict the dynamics very well? And I will try to convince you in the following that actually we have a sweet spot in this wish list, namely considering counts and self-statistics, which compress some of the non-Gaussian information quite effectively, so it has interesting information. We can predict it in an interesting regime, namely the regime of large deviations or rare events that Paulo introduced yesterday. And we have very predictive dynamics because we can use the spherical collapse model there if we are clever about it. So the way you could think about this galaxy survey is you throw spheres and you just measure the mean density, so you get something like this ball pit here, and the color of the sphere tells you how dense it is. So maybe the red one would be very dense, this would be very underdense, and basically you look at the statistics of those average densities in spheres. And of course there's a long history of this idea of counts and self-statistics. I think in cosmology the first person doing it was Hubble, but maybe I'm wrong, so in order not to insult anybody, I will just say the earliest record I found of counts and self-statistics was this year in Ireland. Namely, already the Neolithic people have some record of how to do counts and self-statistics at their, well, astronomical site of the passage tubes. So maybe that's the earliest record you can find. But a lot of people worked on this. Actually, a lot of people are in this room. So I hope I didn't forget anybody, but basically a lot of people worked on this, and I think this shows that it's an interesting point of view. But now there's also a very timely aspect why we should really do it now. On the one hand, we learned from large deviation statistics that we can actually predict this very accurately, and we now really believe that this is some way of going beyond perturbation theory. And in particular, it's analytics, as I will show you later. And on the other hand, there's also renewed interest from surveys we have these days, in particular from dark energy and the KITS survey. People looked at something they called density split statistics. So in some sense, the idea is you look at both galaxy clustering and also their shear. Hence, basically, you also measure weak lensing. And with those joint statistics, you can actually also extract cosmological parameters. And depending on what kind of models you assume there, it might even be competitive to the two-point correlation function analysis. And I think for sure you have different degeneracies there and different systematics. So might just be interesting to do that. But let me now go to the theoretical part. So a small recap of what we're going to use. So the rough idea is the following. If I look at the statistics of densities in spheres, so for example, if I focus on the largest spheres here, I just randomly draw spheres in my final density field. So this is from a horizon simulation. And now I plot, for example, the probability distribution of finding a certain density in this sphere. Then the idea is basically to say, well, statistically, I can relate this probability distribution to the probability distribution in the initial conditions. And I know that the initial conditions were very close to Gaussian. And I'm going to use spherical collapse, not for individual objects, but for the statistics. So that is the reason why I have spheres here. I'm not claiming that any final sphere corresponds to an initial sphere. Just the statistics can be predicted with spherical collapse. And I will make this a bit more rigorous in the next slides. So a quick reminder of why we like spherical collapse so much. So the nice thing is it's basically just matter conservation, and the time evolution is completely specified by Gauss' theorem. So we can write down this evolution equation and we can actually solve it. And you know that in the Einstein de Sitter universe we can find this parametric solution. And essentially, you can think about it. We have this parametric solution that tells you the final density in a sphere towards the initial density or the linearly extrapolated density. So essentially, you can remove this parameter and find a one-to-one mapping between initial and final densities. And this is going to be very useful because this way you can basically map statistics. So what I'm going to use is a very simple approximation to this parametric solution here given by Francis in 92. So the simple idea is I can map the linearly extrapolated density in a sphere of radius little r to the final, so this is the density contrast, sorry, this density contrast to the final density in a sphere of radius big R by using this kind of polynomial model here. So tau is my variable, and nu is a parameter that's close to 1.5. So it's really very simple mapping, but in principle you could also plug in a parametric solution, so it's just for simplicity. And the way I can relate the radii is just by mass conservation, because initial fluctuations were small. Basically I have that the final mass equals the initial mass, which was just given by the radius. So the punchline is here we have a one-to-one mapping between initial radii and final radii, and initial or linear densities and final densities in spheres. So now we are going to combine this with so-called large deviation theory, and I think I don't have to say much more because probably lots of you heard the talk yesterday. But let me remind you of one crucial thing. So what is large deviation theory? Well, we know that in a lot of cases when we do statistics, we converge towards a Gaussian distribution. And if we think about the simplest experiment we can do, we just toss a coin, right? So we record the number of heads or maybe the numbers of tails. And now we can ask how likely are we to actually find a very rare event. So maybe a rare event is we find only one time heads if I toss 100 times. So the interesting point of view is that actually this convergence towards a Gaussian is only true if you're close to the mean. And large deviation theory, although the name might be misleading, basically gives you the correct behavior around this mean, but also in the tails. So it's basically valid across those scales. And the interesting thing is for this coin toss experiment, you can actually just write down how that works. So you toss coins, so you have your Bernoulli sequence. And by using the Stirling formula, what you're going to find is the probability of finding something away from the mean is exponentially suppressed. And this exponential suppression is not given by a quadratic function, which you would expect from a Gaussian, right? This is what you would expect. It's given by some kind of weird logarithmic dependence. And of course, if you expanded this around the mean, you would get exactly that. So the only punchline is large deviation statistics gives you a way to quantify how often will you find rare events, and it's just more accurate than the Gaussian if you're looking in the tails. Because as you can see here, this large deviation result, which is this logarithmic dependence, is clearly different from the Gaussian. So that's basically the only thing we need to use. So now the nice thing about large deviation theories is it gives you a lot of nice theorems that relate different quantities that are related to counts and cells statistics. So very roughly, to summarize what Paolo told you yesterday, if you have the probability of, let's say, densities in spheres, then you call this exponential decay of this probability the so-called rate function or decay rate function. So for a Gaussian, that's very simple. A Gaussian PDF means you have a quadratic rate function. And now the punchline is, if your probability is exponentially decaying, that means if you build a path integral going from initial to final conditions, right? To get the final PDF, you will ask, I have to integrate over all possible paths from the initial to the final conditions. And because of this exponential decay of the PDF, you're going to be dominated by one contribution. And if you have a symmetrical situation, this integral is actually strongly dominated by evolution respecting the symmetry. And Patrick wrote a very nice paper about this. So the main idea is basically if you have something that's exponentially decaying, you can quite easily guess how this exponential decay maps if you have nonlinear evolution. So that's basically the point of view. So we're going to say we know the initial exponential decay, which is a Gaussian, hence this is a quadratic function. And we're just going to map this exponential decay with our spherical collapse model. And now you need lots of mathematics again to deduce the full probability distribution function from your rate function, but I'm not really going to talk about this. So basically you can do clever mathematical tricks to distill the full probability distribution from this exponential decay. And this has a beautiful theory behind, so if you're interested, I'm happy if you ask me. So, but for now the question is, how can we actually use this in practice? So as I already told you, we're going to use Gaussian initial conditions. So we know the statistics of initial densities in spheres at lots of radii. And we want to know the final distribution of densities in spheres. And we're going to fix the radius we want. And we're going to combine large deviation statistics with spherical collapse dynamics. So as I told you, we know Gaussian initial conditions. So this exponential decay is just quadratic function. And what you have here is the linear variance evaluated at the initial radius. And you can already see that this linear variance contains the linear power spectrum, right? This is how I would compute it. So what we do now to get the final distribution, we know it's also an exponential decaying function. And now this exponential decay is roughly speaking just given by plugging in spherical collapse here. So we plug in final densities in terms of initial densities, and we replace the initial radius by final radius and density. And we also need some rescaling that basically maps from the linear to the nonlinear variance. Okay, so if we do that, what do we get? We essentially get a one-parameter prediction for this probability distribution function of densities in spheres. And the one parameter is exactly the nonlinear variance here. So in some sense, you can understand this as a driving parameter of what changes the shape of your PDF. And just to show you what happens, so the analytical approximation I was talking about is if you think about the initial conditions, again, just a Gaussian PDF. So I wrote the Gaussian PDF in a slightly unconventional way. So here you have this exponential with the quadratic function. And in the front, this 1 over sigma is basically just a second derivative of this. So now, roughly, what large deviation statistics tells you, if you combine this with a saddle point approximation, is that the final PDF looks quite similar. So you also have a second derivative here, but of a non-linearly mapped density. So if you're interested in the details, ask me about it. But the point is here, you can go and evolve this PDF, and I just changed the value of sigma from, I think, 0.1 to 1. So if you are close to a very small sigma, your probability distribution function looks rather Gaussian. So this would be mean density here, so it doesn't look too non-Gaussian. Now if you increase the variance, what will happen, you will increase this positive tail here. So basically over densities grow, so the probability becomes way more likely here. On the other hand, under densities basically become rarer and wander to the left here. So they become more underdense and wander to the left here. So that's quite interesting and quite nice to understand cosmic evolution. So either you can say time evolution goes from blue to red, or if I change my smoothing scale, so I change the scale I'm looking at, of course, if I look on very large scales, things will look more Gaussian, so those would be large scales and those would be smaller scales. And the applicability of this formalism is just limited by how big is your variance at the desired scale. So essentially, we want a variance that's smaller than 1, and that roughly means if you go to redshift 0, it's a scale of like 10 megaparsec. So that's basically the scale up to which we can describe this counts and self statistics. Now, of course, the question is, well, I can show you all the plots I want, but how well does this actually work? So what I did here is the following. I used my analytical formula, which has one parameter, and this one parameter I measured from the simulation, so it's basically just a nonlinear variance. And I'm comparing here this one parameter prediction to the direct measurements in Horizon Run 4. And this is at redshift 0.7 for 5 different radii from 10 megaparsec to 15 megaparsec. So again, you can see that larger scales look more Gaussian. And what's quite impressive, that this analytical formula we have for the PDF really remains accurate along 5 orders of magnitude. And it really goes quite deep into the tails. So this is a normalized density that is of order of maybe 5 or something like this. So this is one particular way of probing the nonlinear regime. And this is, of course, great, but now you might say, but this is a logarithmic scale, so maybe I can hide inaccuracies there. So I'm also going to show you the residuals. So this is exactly the same measurements. Here you see the residuals are at the percent level over quite a large range of densities, which I think is really remarkable. So spherical collapse for counts and self statistics is one particular instance where we can really use our nonlinear solution to quite accurately predict the statistics of matter densities in spheres. And just to convince you that it's really an analytic expression, I assumed a power law initial power spectrum and just gave you an impression how this PDF looks like. So what basically enters here is the initial power spectrum. So in this case, just the power law index n. We have the spherical collapse dynamics, which was parameterized through this new parameter, which was 1.5. And of course, it's also driven by this nonlinear variance here. And those are all the ingredients that go in here. And what's also quite nice, you might say, I remember that lots of people said that the probability distribution function of densities in spheres is quite close to a log normal. And this is quite true, and if you look roughly, in particular in a log plot, the log normal looks close. But if you plot the residuals, you can see that the log normal assumption is about 10% or maybe 5% from the true answer. And of course, this also depends on the scale. And this makes sense because the log normal model was a very nice model, but it's phenomenological why we use the theoretical model from first principles. I mean, it's just spherical collapse and Gaussian initial conditions.
What are the error bars of the plots?
So the error bars are basically estimated from the simulation. So we do sub-boxes and just estimate the error bar from that. So now you can ask, what else could we do? So instead of just looking at the statistics of one sphere, you could now draw concentric spheres and basically ask, what is the joint probability of finding a density rho 1 in the inner sphere and a density rho 2 in the outer sphere, or then a density in, rho 1, 2 in the shell. And you can also predict those statistics because, again, you take your Gaussian initial conditions and you map with spherical collapse. And you do a lot of theoretical tricks to evaluate this. And this is quite nice because doing this concentric spheres allows you to prior on certain environments. For example, I could ask, what is the probability of finding a certain density if I already know I'm sitting in an overdense or underdense environment, which is kind of nice. And this can be also used to compute something else, namely counts and cell statistics doesn't only need to be one-point statistics. You could also ask, what is the joint probability of finding a density rho and a density rho prime at a distance r from each other? So this is basically a two-point PDF now. And the interesting thing is, if those spheres are sufficiently separated, you can say that this joint PDF is determined by the individual one-point PDFs, and this we have just computed, and then some correlation. And this correlation now is density dependent. So in general, you would have a correlation function here that depends on the separation of the spheres, their radii, and their densities. But it turns out at large separation, this correlation here basically factorizes into an average correlation function of spheres. So this is just a two-point correlation function smoothed with a spherical top hat, and a modulation of this with functions that depend on the density. And we call this the sphere density bias, but maybe it's better to just call it density-dependent clustering. And some people might be aware of this because people actually suggested something similar, namely the so-called marked correlation function, where you not only measure correlations between two regions, but you also prior on certain density environments. And I think Mark worked on this a bit. So this is quite interesting because, again, we can't predict this two-point correlation here, but we can predict the density dependence of this clustering. So here I show you a plot. So this is the density dependent of clustering. And what does it mean? If you have a large density, then two spheres of large density are more correlated than average. So basically, overdensities are more clusters. On the other hand, underdensities among each other are also more clustered. But if I wanted to combine an underdensity with an overdensity, then they would be anti-clustered. So that is the rough idea. And it's quite nice because, again, we can predict those statistics, so those correlations, from Gaussian initial conditions. So we basically use the result for Kaiser bias. And then we combine it with the spherical collapse to map to this non-Gaussian distribution. And again, it's quite accurate against the simulations. So now you could ask, okay, what is this good for? Well, one particular example, in the same way as you could use the probability distribution function to more accurately measure the variance of the field instead of just sample variance, you can do the same with this joint PDF. So you take your template from this joint PDF, you don't know this correlation function, but you can basically measure this. So you have the template, and from the full PDF, you measure your two-point correlation function. And again, it's more accurate than just doing the pair counting. Okay, so while I hopefully convince you that in principle this is quite interesting, the key question is, how does this depend on cosmology? Because in the end, we want to probe cosmological parameters. So basically, there are a few physical ingredients that go into the model. On the one hand, we have this initial power spectrum that determines the linear variance, and in particular, its scale dependence. So that's the reason why I wrote R here. So it's not just the radius, but the scale dependence of the linear variance. Then we have the growth of the variance over time. So this is basically the growth function. For example, dark energy equation of state would enter exactly there. And on the other hand, the initial conditions enter. So if we were to say we don't have exactly Gaussian initial conditions, we could include primordial non-Gaussianity. And on the other hand, we use spherical collapse dynamics. So for example, if you were in modified gravity or you also included different species like massive neutrinos, the spherical collapse would work differently because basically different components participate differently. So just to show you a couple of examples, what you can do. So if you want to measure the density parameter omega m, this changes the whole variance, so the scale dependence and the time dependence, in a particular way. And one main imprint is actually just in the scale dependence of the linear power spectrum. So here you see there are a couple of % differences. And those differences will also reflect in the PDF. So the point is here, we predict differences in those PDFs that are quite visible. And again, those points are the measurements, and the line is actually the theoretical prediction. So mass density parameter does work. But maybe that's not the most interesting thing, because these days we're in particular interested in probing dark energy. So what can you do for dark energy? Basically, the idea is you measure counts and cell statistics at different redshifts, and you use this growth of the variance that enters there. So this growth of the variance is now dependent on those two parameters if you parameterize the equation of state with omega 0 and W0 and WA. So the rough idea is you just ask, how many redshifts do I have, and how many spheres can I access, depending on what is my volume accessible. And then you can do a maximum likelihood estimator because you have an analytical PDF, so you just write down the likelihood. So we did a very idealized experiment here, assuming we can really measure dark matter densities in spheres, so there's no bias here whatsoever. And you see that you can get quite interesting constraints on the dark energy equation of state, just because you are sensitive to this growth of structure that is correctly parameterized by a PDF. So that's quite interesting. And we also have some simulation measurements that actually our predictions for different dark energy models work quite well. Let me maybe skip the non-Gaussianity. If you're interested in this, ask me about it. Because I really want to talk about the issue of how to go from the theorist's mind. So we had spherical cows because we look at densities in spheres. But they were not like real cows, but like purple cows. So in German, we have the funny saying that people who are from the city might think that cows are purple because Milka chocolate has purple cows. So in the same way, a theorist might think predicting dark matter is like predicting the real world. Well, it's unfortunately not. So the main question is now, how do we go to observables? And of course, one prime observables would be to measure counts in cells just for bias tracers, so for galaxies. And on the other hand, we can think about, can we do weak lensing with this idea? So just generalize our formalism to include weak lensing. Let me first focus on bias tracers. So what we did here was, again, going to the simulation and asking, okay, in the simulation, we can measure both dark matter densities in spheres and halo densities in spheres. In our case, we chose to weight the halos by their mass, simply because if you weight halos by their mass, they are closely related to the matter, right? Because you need to upweight the high mass halos. And just from a very simple idea of including biasing, you could say, well, I can make a scatter plot, right, which basically indicates a local relationship between the matter density in a sphere and the halo density in a sphere, and you get this cloud of points here. If you wonder what this shadow is, so this shadow is if you wouldn't do a mass weighting, just to show that then this cloud is bigger. So, okay, if you do mass-weighted halos, you get this cloud here. So, of course, there's not a real deterministic one-to-one relationship, as Roman already introduced. But the interesting point is now, if we just want to predict one-point statistics, we are not really sensitive to this scatter here. So in some sense, we can hope that we can just find a mean relationship between matter and halo densities in spheres. That would look something like this red line here. And use this mean relationship to map our probability distribution functions. And another way to see this, so you might complain, oh, this is local bias, I don't really believe that, I think it's not nice. You can think about it in another way. You can simply say, if I have two probability distributions of matter and tracers, you could simply choose to abundance match, right? And this is essentially what you can also do, and since the matter and the halos are quite correlated, this abundance matching bias function will also turn out to be a good description here of the scatter plot. And this is actually what I showed here. So this is if you use the cumulative PDF, so that's an abundance matching technique. And the scatter plot fit is almost indistinguishable from this. So now the key question is, how can you find a good description of this mean relationship between matter and halo densities in spheres, right? Because you need a good parameterization. And one problem is that we want to go into the tails. So this local expansions in polynomials is not quite successful because usually this breaks down exactly in the tails. We found that in this case, actually you can find a quite simple parameterization just by relying on the log densities. So this is basically your density in the sphere. You take the log of it, and then you write down a quadratic model. And those different 3Bs are also related because overall mean density is 1. So essentially, this is a 2-parameter model. And this is quite nice because it turns out this 2-parameter model is very good fit to this mean relation you find from abundance matching. And it even includes redshift space distortions. So one way to avoid modeling redshift space distortions, you can just say, well, I measure matter in real space, but the halo densities I measure in redshift space. So this is basically just a very quick check whether redshift space distortions would be absorbed by the bias model we have or not. So you see that actually you increase the scatter a lot. So you might think, okay, maybe the redshift space PDF for halos is going to be worse, but you're going to see in the end that it actually does not matter. So the main message is why in general bias is very, very complicated. The impact on statistics that are counts in cells is usually not very high, mainly because you have a lot of spheres. So usually the stochasticity just averages out. So in some sense you are lucky. And it's also quite interesting because in some way you can relate it to this large deviation statistics perspective, because you say you're going to be dominated by one mean relationship. And in some sense that's exactly what we are parameterizing here. So now, to finally show you results for halos. So this is halo densities in spheres, mass weighted, at two different redshifts, 0 and 1, and two different radii. And those are the PDFs, this time not in the log scale. And those are the residuals if I take my prediction for the dark matter PDF and I just map with my one-to-one bias relation. So it's really just you attach the Jacobian here and you are done. And it's quite impressive because it turns out if you model your bias correctly, you don't diminish your accuracy on the halo PDF. So now the key question is, how do you always accurately find those bias relations? And I will show you again the same for redshift space. And you will see, again, not a big difference. So residuals are very similar. Now you might say, OK, I looked at halos, but I didn't really look at real galaxies. So I found myself very bold of actually looking at galaxies in a simulation for once, being a theorist. So what did we do? We looked at the Horizon AGN simulation, and we measured halos weighted by their mass, and also galaxies, both weighted by the mass of the halo, which in principle, in practice, you couldn't really do because you don't know the mass of the halo. So instead, we tried to just weight them by their luminosity. And this is very nice because in principle, on the simulation basis, you can also include uncertainties at this level and model it. So what you see here is not a PDF, but a cumulative PDF, simply because the box is not very large, Horizon AGN, just because it's very expensive to actually model those galaxies. So the punchline is here. Since we do an abundance matching, the question is basically, how similar is the cumulative PDF of the mass-weighted halos to the luminosity-weighted galaxies? And while this is the dark matter here, so the grayish line, the black dashed in between, the halos are the blue line, and the galaxies are the orange line here. And you can see that luminosity-weighted galaxies are actually very, very close to mass-weighted halos. Hence, we would expect that our bias parameterization maybe even work for galaxies. And since you might say, well, that looks suspicious, so of course, if you look at galaxies, your scatter is way larger than for halos. But again, the scatter does not manifest itself in this one-point statistics. It basically averages out. So, since I'm almost out of time, I want to do a short advertisement of a talk next week. So I was working with a student in Cambridge, Oliver Leicht, and we are thinking about how could you generalize this counts and self statistics to access more volume. More volume is at high redshift, so what kind of high redshift traces can you find? And he's going to tell you a bit about how you could think about doing intensity mapping with counts and cells, namely using neutral hydrogen as a different bias tracer. But for now, in my last, hopefully 5 minutes. Okay, very good. I want to mention a different idea. So far I focused on bias tracers and told you if you have a good bias model, you can include this in your description. But of course, in the end, it would be way better if we could actually access weak lensing statistics, right? Because we don't have bias, and we are really just sensitive to the matter field. The downside is, of course, that the weak lensing statistics is intrinsically integrated, right? Because you are basically sensitive to all the mass starting from a given redshift to the galaxy that you use as a source. So as a first step, we looked at densities in cylinders because you think about weak lensing as basically having different cylinders of matter and then just weighting them if you integrate it. And also for cylinders, you can find a good theory. But now the question is, what could you imagine doing if you have both weak lensing and also tracers like galaxies? And there was a very nice paper by the desk collaboration. So it's Oliver Friedrich and Daniel Grün. And they called it density split statistics. So the idea is very simple. In principle, you use counts and self statistics for galaxies, and you add lensing information by doing so-called lensing in cells. So it's basically you look at the matter density in cones weighted by the lensing kernel. So what you do here, you basically look at your galaxy field, you divide it in 5 different quintiles. So you have basically overdensities and underdensities. And now you look at the signal of the tangential shear. So this is basically sensitive to all the matter around. And you see a clear signal here, and the point is you can see it's different from Gaussian and actually well modeled by Francis' model from '94 using perturbative results. So in principle, they showed that doing this joint lensing in counts and cells is in principle possible with this idea. And we are hoping that in the future we can improve on this by basically relying on spherical collapse and going a bit beyond perturbation theory. So this is very nice that you can do that. And just as a final conclusion, you can show that if you do this joint lensing in counts and cells and you look at the constraining power, in principle, you can be competitive with the 3 times 2-point correlation function, but this crucially depends on what kind of parameters you need for your bias model. So this is the reason why you see 3 different contours here. So the simplest one is you basically just need a linear bias. And for the galaxies they probed, it's a way smaller range of density, so it's actually turned out to work quite well. So this would be one parameter, just linear bias. The green line would be linear bias and stochasticity because, of course, you sample the galaxy field not quite continuously. So basically, you could think about you have a Poisson sampling, and then this R encodes the stochasticity. And if you have an even more complex distribution that's non-Poissonian, then you can parameterize with those 2 extra parameters here. So the basic punchline is, depending on how well we can understand this bias relation, in principle, we can hope that with joint lensing in counts and cells, we get competitive results with the 2-point correlation function. And as I said in the beginning, they will depend differently on systematics, and I think will be a very nice cross-check. So let me quickly wrap up. I hope I convinced you that counts and cell statistics are interesting and actually one playground where we can really take advantage of the nonlinear solution of spherical collapse to get % accurate predictions for densities in spheres above 10 megaparsec. And that's quite remarkable because it's really an analytical theory. So then we of course need to assess what is the cosmology dependence, and I hope I convinced you that there's interesting cosmology dependence in this PDF, hence we can probe cosmology if we look at this. In order to really use that in practice, of course we need to include lots of effects. One of them is galaxy bias, redshift space distortions, or we need to approach weak lensing observables. But I think it's quite encouraging because the prospect to really get competitive results to two-point correlation functions or just complementary ones is going to be great. So thank you a lot.